So today we're going to talk about gas stoichiometry, right? So we've already used stoichiometry to go between grams and moles and even milliliters and liters of aqueous solutions. But today we're going to talk about how to deal with gases. So when the product of a reaction is a gas, how can we predict how much of that gas we're going to make, what the volume will be, what the pressure will be, how many moles we're going to make, all of that stuff. The first thing we have to understand, what makes gases unique is unlike liquids and solids, because gases are so spread out that they fill their entire container, the size of the particle or even the identity of the particle doesn't matter. As long as we're talking the same pressure and temperature, all gases occupy the same volume, meaning a mole or a half a mole or whatever amount you want to talk about of oxygen will occupy the same amount of volume as a mole of hydrogen, even though hydrogen is a lot smaller. And that's because the size of the particles is so many, many thousands of times smaller than the distance between the particles. So another way of saying this is that at STP, which stands for standard temperature and pressure. In standard temperature, we use 0 degrees Celsius or 273 kelvins. And pressure, we already know standard pressure is 1 atmosphere, 760 mmHg, etc. So at those conditions, 0 Celsius and 1 atmosphere, 1 mole of any gas, regardless of its identity, occupies 22.4 liters. So when we've worked with gases in some of our water displacement labs, and you get these really, really small number of moles, well, it kind of makes sense because gases are not very dense. So if you're only creating 50 milliliters of a gas, that's not going to be anywhere close to a mole under normal standard conditions. So it would take 22.4 liters in order for us to have a full mole of a gas at 0 Celsius and 1 atmosphere. Okay? So the first question says, how many liters of nitrogen would be required to produce 350 liters of NH3? So we're looking for liters of nitrogen. Okay, and it does give me a pressure and a temperature. And in some gas stoichiometry problems, those are going to be helpful because they allow us to use the ideal gas law to solve the problem. But in this case, because both the thing that I'm given, the NH3, and the thing that I'm asked for, the N2, those are both gases. Okay? And since a mole of any gas occupies the same amount of space at any temperature or pressure, one very important thing that we can take from that is we can look at our coefficients, which for nitrogen would be 1, and for NH3 it would be 2. If those are both gases, that is not only a 1-to-2 mole ratio, but that's also a 1-to-2 liter ratio. Because when it comes to gases, it doesn't matter which gas we're talking about, 1 mole occupies the same number of liters. So therefore, my ratio of moles is also my ratio of liters. What that does in this problem is it allows me to just focus in on the volume and go straight from liters of NH3 to liters of nitrogen. Let me show you what I mean. So I've got 350 liters of NH3. All right. Now, normally we might think, okay, I can now take the pressure and the temperature and use the ideal gas law to convert this into moles and then maybe do some stoichiometry to get to my amount of nitrogen. But again, since they're both gases, we can use the coefficients in the balanced equation to go straight from liters of NH3 to liters of nitrogen, right? And so those coefficients are 1 and 2, right? And so all I'm going to do is 350 divided by 2, which should give me 175. So I would expect to need 175 liters of N2 if I was trying to make 350 liters of NH3. So it's a very simple, straightforward question. Okay, the next question is a little different. It says how many grams of methane, which is CH4, would be required to react with 44 liters of oxygen at STP. Okay, so let's start by coming up with a balanced equation. So it's CH4 reacting with oxygen, which is O2. So see if you can remember what kind of reaction that is and what our products would be, and then balance. Okay, so hopefully you said CO2 and H2O would be our products because it's combustion of a hydrocarbon. And then to balance hydrogen, I would put a 2 in front of water. And to balance oxygen, I would put a 2 in front of O2. Okay, so we're going to go from liters of oxygen, and we're going to try to take that to grams of CH4. So in order to get grams of CH4, I would need moles of CH4, right? And in order to go from liters of oxygen to moles of CH4, I would first have to find my moles of oxygen, right? So we're just kind of planning out the problem, right? The second part of this is the stuff that we've already done, moles to grams. We did that in our stoichiometry unit many, many times, right? The first part, going from liters of oxygen to moles of oxygen, is a little different, okay, a little new, but it can be done pretty easily because we're at STP. And notice up above we said at STP, 1 mole of gas occupies 22.4 liters. So that sounds like a relationship I can use to solve this problem. So if I have 44 liters of O2, and I want to convert that to moles of O2, just like my plan says, I can use the fact that I'm at STP, okay, and this only works if I'm at standard temperature and pressure. I know that 1 mole of a gas occupies 22.4 liters, okay? And so liters goes away, and now I can go from moles of oxygen to moles of methane. And at this point, it becomes just like any other stoichiometry problem. We go from moles to moles using the balanced equation. So we have a 1 to 2 ratio. And then we go from moles of CH4 to grams of CH4 using the periodic table. And it should be about 16.05 grams. And so now I just get out my calculator, and I'm going to say 44, we'll just make this one big fraction, 44 times 16.05 on top, and then on the bottom 22.4 times 2. And that gives me about 15.76, or we'll say 15.8 grams of CH4. Okay, let's take a look at the last problem. How many grams of calcium chlorate would be needed to produce 125 milliliters of oxygen gas by water displacement at 102.5 kPa and 21 degrees Celsius? So we start with our balanced equation. I'll help you with this one. Calcium chlorate is going to be CaClO3 2, and it's going to produce calcium chloride and oxygen. And then to balance this, it looks like we just need a 3 in front of oxygen, right? So there's our balanced equation. Okay, so in terms of our plan, we are starting with milliliters of oxygen, so milliliters of O2, and we're trying to get to grams of calcium chlorate. Okay, so we can plan in either direction. One way to go would be to say, well, I know I need to get to liters of O2, and then from liters of O2, I probably need to get to moles of O2, and then to get to grams of calcium chlorate, I probably need to get there from moles. And so it looks like these two would kind of bridge the gap there and go straight from moles to moles. Now, all of this is pretty much, the second part of this, I should say, is just stoichiometry, going from moles to grams. We just did that. But the first part here, well, milliliters to liters is just simple little one-step conversion. But then liters to moles, in the last problem I did it using my 22.4 number. But in this problem I don't think I can do that because I'm not at standard temperature and pressure. But there is a different way to find moles from liters of a gas. And that is using the ideal gas law, right? So PV equals nRT can be rearranged to solve for moles, right? N equals PV over RT. So go ahead and see. Now, the other thing I want to point out here is, since we're dealing with two different substances, sometimes it's helpful for us to label not just N, but N of O2, right? So we're specifically looking for moles of oxygen. We don't want to get confused and think that this equation is going to find us moles of calcium chlorate, right? Because if the liters given to us is for oxygen gas, then the moles that we find from that will be for oxygen gas, not calcium chlorate. So go ahead and see if you can find the number of moles there. Pause the video and give it a shot. Oh, and I'm sorry, don't forget that if it's collected by water displacement, we have a little subtraction we have to do. Okay, so now I used the ideal gas law and I found my moles of oxygen. I didn't show this part, but I did go ahead and divide 125 by 1,000 to get my liters, because it was 125 milliliters, but I just kind of did that in my head by moving the decimal. But that is important, so make sure you've done that. Also make sure you've converted your temperature to kelvins, and also make sure that you go to your table, because we're collected by water displacement, to get the number to subtract on top. So that's my number of moles of oxygen. And so the last two steps are simply to go from moles of oxygen to moles of calcium chlorate, and then grams. And that is stuff that we've done many, many times. So go ahead and, again, pause and give that a shot, and then come back and check your answer. Okay, and there you have it. I just did stoichiometry the rest of the way. You can see it there in red. I used my 1 to 3 molar ratio from the balanced equation, and then I went to the periodic table to find my grams per mole of calcium chlorate. And then when I multiplied by the molar mass and divided by 3, I got 0.353 grams of calcium chlorate that would be needed to make those 125 milliliters of oxygen gas. All right, make sure you come into class with specific questions so we can be productive as we go over this and do some more practice.